Welcome to Physics 371 Online. I'd like to work out an example where we use the separation of variables method to solve a problem in spherical coordinates where instead of being given the value of the electric potential on some surface, we're actually given the charge density. There's an example worked out in the textbook like this as well, but mine's a little bit simpler, and so it will give us an answer that we already know what to expect, and so we can check it really easily. And here's the problem. A spherical shell with a radius r has uniform charge density sigma. Find the electric potential V inside and outside the sphere. And so here I'll just draw a little sketch to show the spherical boundary, right, with a radius r. And we are given the charge density on that surface. You have a homework problem where the charge density specified on the surface is a little more complicated than this, but this problem is really simple, and so I can work it out pretty quickly and illustrate how this kind of problem should be approached. Well, first of all, remind ourselves we're trying to find the solution of Laplace's equation, and we already know that there is a specific form for the solutions to Laplace's equation in spherical coordinates, and so it's not too difficult to remind ourselves what those are, because we've already applied some of the boundary conditions that have to be met for these solutions. So we know that inside the sphere, the general solution of the potential is an infinite series that looks like this: a sub L, r to the L, p sub L of cosine theta, where remember the p sub L functions are Legendre polynomials. Then we have an expression for V outside the sphere, where there's an infinite series again that has B sub L over R to the L plus 1 times these Legendre polynomial terms. And I'll just write down again the limits on the sum. The indices run from 0 to infinity. So these we already know by application of the boundary conditions at the origin and as r goes to infinity. So these are starting points that we can use in problems of this type. Now you'll see that there's no obvious connection between the potential and the charge density on the surface, but we'll figure that out in just a minute. First of all, let's apply the boundary condition at the surface of the sphere, where we know V in and V out have to match up. So what I'll do is substitute in little r equals big R in both of these expressions and set them equal to each other. So we've got inside the sphere, we've got the sum a sub L, capital R to the L, and I'll abbreviate the Legendre polynomial by just writing P sub L. Cos theta is the argument, but for simplicity we'll just write it like this. Okay, and then outside the sphere we've got the form that has B sub L, and now we plug in big R to the L plus 1 power and multiply again by the Legendre polynomial. And so these sums have to match up, and it's easy to show, although I won't do it here, that the coefficients, the terms that multiply the Legendre polynomials inside these sums have to be equal. So in other words, this term here has to be equal to this term here for each value of L. And as a result of that, I can write down the really simple relationship a sub L r to the L equals B sub L over R to the L plus 1. And if I use this to solve for B sub L, I see that it's equal to A sub L times R to the 2L plus 1. And what's nice about this is it really means all I need to do is solve for either A sub L or B sub L separately, and then I can get the other ones. And if I get all of the A sub L's and B sub L's, then I in principle know what these solutions are, and I'm done. So that's our goal. But how do we approach this kind of a problem where we're given the charge density instead of some kind of function for the electric potential? And the way we do it is to remember this is something originally we encountered in Chapter 2, and then we came back and looked at it at the beginning of Chapter 3. So at a surface that has a charge density sigma, there's a discontinuity in the electric field. And that discontinuity can be written down in terms of derivatives of the electric potential. So in this case, dV out by dr minus dV in by dr evaluated at little r equals big R, in other words, evaluated at the surface, that discontinuity has to be equal to minus the charge density over epsilon 0. And so for where this comes from, you can refer back to chapter 2 of the textbook. But what's nice about this is it makes a relationship between some function involving the potentials inside and outside and the charge density that's on the surface. So what I will do is take the two expressions for V in and V out, take the derivative of each term in the sum with respect to r, and then we'll plug in little r equals big R, and then we'll set the left-hand side equal to the right-hand side. And we'll see where we go from there. So, first of all, dV out by dr, that's this term here. So that means it's going to still be an infinite sum from 0 to infinity, and what this really is B sub L times little r to the minus L plus 1 power. And so when we differentiate, we'll get the power, which is minus L plus 1, right? And then we'll have the B sub L, and then the exponent gets larger by 1, and so that will give us a r to the L plus 2 power. All right. Again, if this is a little bit, and then we've got the Legendre polynomial as well. If this is a little bit fuzzy, just think of this as r to the minus L minus 1 power, which is what this denominator is, right? So that then when we differentiate it, then it becomes, the power comes down in front, which is what I have right here, minus quantity L plus 1, and then the exponent gets increased by 1, and so we end up with this kind of expression here, in the same way that the derivative of 1 over r, right, is minus 1 over r squared. So this has that same kind of property. So that is dV out by dr, and we'll have to evaluate it in a moment at little r equals big R. But first we subtract off what we get for dV in by dr. And this one's a little bit easier because we see that we get L times B sub L times r to the L minus 1 power. And so multiplying again by the Legendre polynomial term. So those two sums give us now what's on the left-hand side of the equation here, and that's got to equal minus sigma over epsilon 0. But now I plug in the capital little r equals big R, and so then I'll combine these all into one sum because the indices are the same. So we go from 0 to infinity. The first term is it's minus L plus 1 B sub L over capital R L plus 2, and then I'll pull out the Legendre polynomial term because it's common to both of these. So then I have minus this one. Ooh, you know what I did wrong? This term here, you might have noticed this as I was doing it, this term here actually should be A sub L. And so I'll just fix that. Right, it should be minus L times A sub L, r to the L minus 1. All right, so now we can fix that. Minus the quantity L times A sub L times capital R L minus 1 power. Right, so now we've substituted in the little r equals big R, and now we've got the Legendre polynomial. So that whole sum has to give us minus sigma over epsilon 0, like that. So did I make any mistakes yet in this? No, that looks good. Okay, so what we can now do is substitute in for the B sub L expression here that will allow us to simplify the problem. We know that the b sub l term is equal to a sub l times capital R to the 2l plus 1, right? And so if we do that, then we'll see that this summation can be written 0 to infinity minus L plus 1. Now here b sub L is a sub L capital R to the 2L plus 1, and now this whole thing is still divided by R to the L plus 2, right down there, minus L a sub L capital R to the L minus 1 power, right, times b sub L equals sigma over epsilon 0. Okay, now what we can do here is clean things up just a little bit on the left hand side, and as I scroll down on my tablet here, I'll get some more room. So the sum is still the same, and I will pull the a sub L out in front and then collect all these other terms. So we have a sub L, and we've got negative L plus 1, and then the term with the quotient of the two R terms here gives me R to the L minus 1 power, right? Because when we have the quotient of two terms with exponents, we just subtract the exponents. So it's going to be R to the quantity 2L plus 1 minus the quantity L plus 2. And so that gives us this. And then we're left with minus L times capital R to the L minus 1 power times our Legendre polynomial term. All right? Now we're making progress. And what we should see here is that what's on the left-hand side is going to be a series of terms all added together that all have successively higher powers of cosine theta. The p sub L, you know, of course you remember that p sub 0 is just equal to 1. P sub 1 is just equal to cos theta. P sub 2 is 3/2 cosine squared theta, right, minus 1/2, and so on and so forth. So the P3 will have a cosine to the third power and a cosine to the first power, and so on. What we see right away is that on the right-hand side, the only kind of term that we have is a constant term. And so we don't have any powers of cos theta. So as a result of that, when we start to write out the terms on the left-hand side, we will see right away that we're only going to need a very small number of terms, maybe even just one term on the left-hand side, to match the constant term that's on the right-hand side. Okay, oops, and you know what I did? I dropped the minus sign, so I'll fix that. I'll put that back in here, like so. Okay, so this is actually going to be a pretty easy task. So now write out, and I'll just say the first two terms on the left-hand side, and then we'll put a dot in to remind us that there are more terms, but it's pretty easy. So what's this going to do? Now the L equals 0 term will give me A0, and what this is going to have, let's see, negative 0 plus, so it's a minus R to the minus 1 power. That's what we get by plugging in L equals 0. The second term will just be 0 because L is equal to 0. And so P sub 0 is just 1. So that, now we add another term. Now we're going to have an A sub 1 term. A sub 1 for L equals 1. So that'll give us a minus 2. L equals 1 gives R to the 0, which is just 1. And then we have minus L equals 1, minus 1 times capital R to the 0 again. All right, so it's just negative 2 minus 1. P sub 1 is cos theta. All right, and what you see here is I know right away that this A sub 1 term is going to have to be 0 because there aren't any cos theta terms on the right-hand side. And the same sort of thing will happen with the A2 and the higher order terms. All right, so I'll put them in here, dot, 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 but we know that the only term that will be non-zero is the A0 term, because the A1 term goes to 0, A1, A2, etc. all equal 0, leaving behind just the A0 term. So as a result, we'll put a therefore here, A sub 0, so in other words, negative A0 over R, which is this first term on the left, equals negative sigma over epsilon 0. Therefore, A0 is equal to sigma R over epsilon 0. And that's the only A that we have. And now let me just scroll back up for a moment so that you can see again. We now know what the B0 is. B0 is equal to A0 times capital R to the 1, right? Just capital R. So B0 is A0 times R, so that's just sigma R squared over epsilon 0. And we are almost done with this, right? What we can do now is just go back to our original expressions for the V in and V out that we know from up here and write down what the solutions are going to be. So give me just a second here. I will erase a little bit to create some room. But I want to leave the original expressions for V in and V out up there, right, so that you can remember where they come from. So what am I doing? I'm going to plug in just A0 as sigma R over epsilon 0. So V in, which only has those A0 terms, V in is just sigma R over epsilon 0. That's the A0, and then we have R to the 0, which is 1, P sub 0, which is also 1. So that's V in. It's a constant, right? Constant. Nice and simple. V out, the only one that we plug in now is B0, which is sigma R squared over epsilon 0. So we're going to plug it into this term. V out is, well, we've got, there's going to be a, for the L equals 0 term, which is what we have, we'll have R to the 1 in the denominator, little r to the 1. So we have sigma R squared over epsilon naught times R. All right? And this has the form 1 over R, which is what we would expect for a point charge, right? And this spherical shell is acting just like a point charge for this kind of situation, because when we're outside of it, right, it's got spherical symmetry, and we know from some of our earlier Gauss's law problems that that's going to give us an electric field and an electric potential that are identical to that a point charge centered at the center of the sphere would give us. And you can even check that out. Matter of fact, I'll go ahead and do that because it's really easy to check out. If we wanted to see, does this solution match the expectation that we would have for a point charge, it's easy to do because, right, V point charge is, right, the Q of the charge over 4 pi epsilon naught times R. That's easy. And for this problem, what's the Q? Right, the Q for a spherical shell would be the surface charge density sigma times the surface area, which is 4 pi R squared. Okay, so Q here is sigma 4 pi capital R squared for the shell. And so we'll plug that in to the point charge equation, and we get sigma 4 pi R squared, right, over 4 pi epsilon naught R. The 4 pi's drop out, and we end up with sigma R squared over epsilon naught R. And that matches exactly what we had for V out. Okay? So this is nice confirmation that the method that we've used here, although it's not the only method we could have used is correct. We get the same answer we would have expected for a point charge outside the shell. So I hope this is helpful. Just to review what was different about this problem, instead of being given in the original problem the potential on the surface of the sphere, we were given the charge density, and here is what we did. We relied on this relationship that tells us that when you're at a surface that has a charge density, there's a discontinuity in the electric field, and that means there's a discontinuity in the derivatives of the electric potential. So we plugged our expressions for V in and V out into this, we took derivatives, and that related the A sub L's and the B sub L's to the charge density sigma. So we'll do more of these in class. You'll have more chance to practice on these for homework problems, and I hope this was helpful. I'll see you in class.